Hello everyone, welcome back to 3 Deviations. In the last video, we covered some of the examples with sine and cosine integrals when we had integrals involving sine to the n of x times cosine to the n of x dx. Well, in today's video, we want to deal with integrals where we have the tangent to the m of x times, or maybe we have an m there, and secant to the n of x dx. We talked earlier also about the relationship that sine and cosine have, and that the relation that tan and sec have as well, and obviously cosecant and cotangent. And this is because when we differentiate tangent and secant, we get functions involving the other. So, for example, the derivative of tangent is secant squared. So that's where we kind of get those relationships there. So in the last pair of videos, we dealt with sine and cosine. Now we're going to be dealing with tangent and secant. So we're going to go over the formulas, and we'll do a video with examples. It's going to be the kind of same shtick. We're doing that 3 times. So we'll be dealing with that, and we'll get started now. So let's start by just integrating tangent. We haven't gone over the integration of tangent yet, but it's something that we can do, and it gives us good opportunity to practice our u sub skills. So let's do this. So we say that the integral of tangent of x dx is equal to the integral of sine x over cosine of x dx. What we do now is we set a u substitution, set u equal to cosine of x du is negative sine of x dx. This gives us the integral of negative du over u, or negative integral du over u. That gives us negative 1 times the natural logarithm of cosine of x. With our logarithm properties, we can pull that negative 1 out and turn it into the exponent. And if we do the reciprocal of the cosine, that becomes the secant, so that gives us the natural logarithm of the secant. Really don't care if you say negative natural logarithm of cosine or the logarithm of secant, it's fine. And then obviously we add our arbitrary constant of integration right in there too, which is always important. And let's also just really quickly go over the integral over the cosecant. We're not actually going to derive this. This is something that's going to come later. So we're going to be doing trig integrals. We're coming on the end of that soon. Then we'll be doing trig substitution, which I think is probably the hardest that we're going to be dealing with. Then we're going to do the Weierstrass substitution, and that's how we integrate the secant and cosecant, and we'll deal with that later. That's all to come. But I'll just give you the integral of the secant right now. The integral of the secant of x dx is equal to the natural logarithm of the absolute value of secant x plus tangent x plus c. So we get, again, that relationship between the secant and the tangent right there. We're integrating secant, and we get something of tangent and secant. And then we get that natural logarithm, of course, adding plus c at the end. So that's the integral of the secant. All right, so now let's go over our cases. Again, we're going to do that whole shtick again. So again, let me just rewrite our Pythagorean identity for tangent and secant. This says that the tangent squared plus 1 is equal to the secant squared. And I know I'm being horrible, I'm not putting in the arguments, but we can save space and save time. So that's what we get there. So let's say I'm integrating the tangent to the m of x times secant to the n of x dx. Let's say we have the case where n is equal to 2k, so the power of secant is even. So if the power of secant is even, then what we're going to do, as you remember from the sine and cosine, we're trying to get into a place where we can do u sub and use the Pythagorean identity. So we get that the integral of tangent to the m of x times secant to the 2k of x dx is equal to the integral of tangent to the m power of x, and then we take out a secant squared, and then we use the rest to put into a secant squared here, times secant squared of x to the k minus 1 power times secant squared of x dx, right? So now we've got a tangent that we can set equal to u, and we've got the secant squared, which is the derivative of the tangent, and here we can replace this so that that becomes 1 plus tangent. So we get the integral of tangent of m of x plus 1, or times 1 plus the tangent squared of x to the k minus 1 power times secant squared of x dx. So we set a u substitution, set u equal to tangent of x, then du equals secant squared x dx. Then we have du here, we have our u, then there we go. All right, let's try the next case. This is our last case. We don't have many cases here. But so we have the integral still of tangent to the m of x times secant to the n of x dx. So now we're going to say that the m is odd. So the power of the tangent is odd. So m equals 2k plus 1. That's all that matters. Again, I'll write down our identity here. Tangent squared plus 1 equals secant squared. So what we do is we do a similar kind of thing, getting to that Pythagorean identity. We do tangent to the 2k plus 1 of x times secant to the n of x dx is equal to the integral of tangent squared of x to the kth power times secant to the n minus 1 of x times secant x tangent x dx. That's equal to the integral of secant squared of x minus 1 to the kth power times secant to the n minus 1 of x times secant x tangent x dx, right? So now again, we set u equal to the secant of x, thus du is equal to tangent x secant x dx. So here we have our du already right in there. Then we are going to have some u term here, another u term here, it's 1. So then this becomes an algebraic, this is so messy, term that we can deal with. I can't look at that anymore.